Recapping a little bit, remember what we're trying to do. We're now doing the second part of this if and only if proof, and effectively we're trying to show that a grammar can be made, can be constructed in such a way that it behaves like a PDA. Now in the first half of the proof it was the reverse. We had a PDA that was behaving like a grammar. So this second half, well, second part, because it's more than half, is quite a bit harder, and like I was saying before, it'll take more than a board to get through it. So what you'll do this session and the next, you won't see the point of it yet until the next board. So concentrate on picking up the tools that later will make sense. You'll see why they're presented. Right? Now, in trying to create this grammar, this CFG that behaves like a PDA, one of the first tools was that for every pair of states, little p and q, in the PDA, well, let's just call it P, so the machine P, and the grammar is G. So we'll just talk about P and G to the end of the proof. So for every two states, for every pair, little p and q belonging to big P, create a new variable belonging to the grammar G, and label that new variable capital A suffix PQ. So A PQ, right? And this variable, it has the property that when you expand it out using the rules of the grammar, using the substitution rules, it will generate all the strings that that you can generate, starting at a state P with nothing on the stack, and ending in state Q with nothing on the stack. Because remember, we're getting a grammar G to behave like an automaton, a big P. Right? Now also, these strings, all these strings that you're generating, they will also take your machine P from state little p to little q without, I mean, the stacks don't have to be zero, empty at the beginning and the end. I mean, if you these strings would take you from the same, like if you're in state little p and you had something on the stack, well, that A PQ, the strings they generate would take you would take the machine, the automaton P, would take it to state Q with the same contents on the stack as it had when it was in state little p. Okay, little computation. All right. Now we're going to now remember we're trying to get a grammar to behave like a machine P. So we're going from G to P. Before we went the other way, but this time we're trying to get a grammar to behave like a machine. So we're building G. We're building the grammar so that it behaves like P, like a PDA. Right. So this machine that we're going to build, this P. So we start with G. I'm going to build a P. Well, to make things a bit easier, let's modify the P somewhat. we'll simplify it. We'll give it a certain property or 3 features. For a start, it just has one. That can't be right. A single start state, CntxtFreeLangs. That sounds crazy, doesn't it? Let me just check that I made a mistake. Yeah, accept state, I thought so. Okay, it has a single accept state. Right? Just one accept state. Right? This P that its second feature is that it empties its stack before it accepts. Okay, so when it accepts, it has an empty stack, and when it performs, when it operates, it does not do a push and a pop at the same time. It only does one or the other. Okay, so an action, if you like, a move on the part of this machine, P, it's either a push or a pop, and that's it. Okay, so where the grammar that we're trying to generate, make it behave like a machine P. Well, our target, the P, we're giving it these special features. It just makes it easier to create the grammar by doing these, as you'll appreciate later. So your P is a little bit special, right? It has these features. Right now, giving the machine these 2 characteristics is pretty easy, right? Well, you just have one accept state. And 2, how do you make it empty its stack before accepting? Well, you just keep popping until it's empty. All right. Okay. Now the third one, how to make our P, our machine, only push or only pop. I mean, at each move, it can't push and pop at the same time. It can only, at a given time, it can only either push or pop. Right? So how to do that? Well, we can so in the original T, P, the original machine, we can modify it in such a way that if you have a transition that pushes and pops at the same time, so effectively overwrites the top of the stack without the symbols below moving up or down. So we don't want that, and you'll see why later why we do that. Okay, so you can change that transition that does simultaneously push and pop by having 2 transitions, one after the other. So you add a state, you have a supplementary state that will allow you to do that. And in one of the transitions you push, and the second transition you pop, or vice versa. Is the order important? Well, if it's pushing and popping at the same time, effectively it's just overwriting the top symbol. So if you push or pop, doesn't matter the order, whether you pop or push or pop. Is that true? Is that true? Well, you should think about that. Okay. So now, if you have a transition that neither pushes nor pops, doesn't do anything, you can model that as well with this modified P that has this feature that it can only either push or pop. So if you have a transition in your original P before you modified it that does not push or pop neither, well, you can use this modified machine, P dashed if you like, well, you can have it push and pop a dummy variable, a dummy symbol, an arbitrary, an arbitrary stack symbol. So that would be the same. All right. Now, remember our grammar. We're filling it with variables, A, P, Q. They're variables, okay. And remember, I'll keep saying it for reinforcement because we're going to need it later. These variables, they're variables in a grammar. Variable, so they belong to a grammar, and when you substitute these, you end up with a whole bunch of strings. Now these strings, they will take the automaton, the machine, P, from state little p to state little q without changing the stack. Right? If you start with an empty stack, you end with an empty stack. Okay. So that's what these do. Right, so that's what's being said here. Now, to go further, to analyze these variables further, we need to focus a bit more attention on what the machine P, the automaton P, is doing when it's operating on these strings. Right? It's an automaton. It's looking at the string symbol by symbol. Okay. And now what's it doing? Now this machine, this modified P, it can only push or pop at each transition. Okay, can't do nothing and it can't do both. It's either got to push or pop at each transition. Important remark. All right. Okay. So let X be one of these strings that this variable generates. Okay.